Hey, what's up, guys? Yeah, so this is my complexity theory series. Yeah, so I want to talk about Ladner's theorem in this video. So basically, so this video will be using the exponential time hypothesis to prove Ladner's theorem in a future video that I will directly prove this theorem. Okay, so basically the theorem just say that because right, so because most of people believe that P is not equal to NP, but so there's a bold conjecture that one can just directly make this that whatever problem is not in P, maybe NP complete. But later in the theorem tell you that if you're under assumption that P equals NP, do not equals NP, there's indeed NP immediate. So basically there's a language L, right? If this is P, this is NP complete, there will be something in the middle. Okay, so this is non-NPI, this NP intermediate will be non-empty. Okay, so you can construct such language artificially, and it's interesting. Okay, this proof is not it's non-trivial, very non-trivial. If you directly try to prove its original form, you need to use the diagonalization. But in this video, let's do some trick. So we can assume that there's a exponential time hypothesis. Basically, it says there's no delta greater than 0, such that reset can be solved in the 2 to the n delta time. Okay, so let's just tell you that you cannot solve reset in the any 2 to the n delta, any linear n time or any linear time is any only exponential. Okay, so if we use this, then we can easily create the proof is very trivial. Proof you can create such one that this Ladner theorem. You can create such language. So the idea is that you can define your language to be L, where X, you need to pad to do some padding. So the idea is that let's say you just create like 1 to the 2 to the square root n, okay, where X belongs to 3 set. So this idea is that you just you just interpreted the 3 set formula as some string and put in the middle one, and then let's say X is length n. And then you just pad this with 1 to the 2 to the n square root n. So you get 1, 1, 1, 1, 1. There's a lot of 1. The length of 2 to the square root n. And then you design this is called language L. So this language L is basically just this. Okay. And obviously, L in NP. Okay. The proof is very simple, right? You just you can just check that the first check whether if somebody give you the input L, you just check whether give your input, you just check y is the form of x1 to the square root n. If it's not a form, then you just reject it. If it's the form, then you because let's say this is length, let's say this is capital N. Okay, so we will keep using this n. So this capital N, you just need to scan it linear time, right? And for capital N, then you can find x is right, and because x is NP, 3 says NP, so you can if you check first you check it, and the second is that you can you spend like linear time, then you can figure out linear time in the input n, you can figure out the x, and the 6x is reset. So you can if there's a satisfiable assignment, then you just check it. So you just check it whether there's a you just check it as satisfied assignment. Okay, so this guy's in NP. Okay, so now so we need to prove that the rest two things. First is that L is not in P. Okay, and the second is we need to prove is that L is not in NP complete. Okay, so L is in P is very simple. You just so prove by contradiction. You just assume that let's assume. So we assume that one can solve L, right? So let's say one can solve L in n to the c time. Okay, that big O. So so sometimes I will ignore big O, so I just write n to the c. Right? Okay, so you see. Okay, and so we want to make that suppose one can solve this determinist L in let's say capital N input and then find and to C, then we want to derive that we get some contradiction on the set cannot solve in the sublinear time. So the fact is that sorry, so we have this. Then we claim that one can solve 3Z efficiently. Okay. Why? Because you can just do because you can first check the input, just check the input. So I say you just need a big O(n) time to find the input. Then you just check it, right? So you first run big O(n) input. Okay. Then you can check whether because what you're saying is that one can solve L in the N to the C, right? So let me just okay. Actually, we don't need this. Okay, so you can first check the input O(n) and assume one can solve L in N to C. So basically, it means that one can solve. So one can solve 3Z in O(n) to the C time, right? Because by definition, right, L the first coordinate of L is the x is 3Z. But you can solve the total L in the N to the C time, so you can solve 3Z in capital N to the C time. Okay, but we know that okay, so there is an important formula, right? So we know that the length of N is basically length of X plus 2 to the square root N. And this is N, so which tell you that the capital N is just basically approximate 2 to the square root N. So if this is true, that means that one can solve 3Z in O to the 2 to the square root NC time, which is contradiction, right? Because we say that this big O this 3Z cannot solve in 2 to the delta N time. Okay, and obviously that 2 to the square root and C big O is less than the big O of 2 to the delta N. Okay. Now the second part is that we need to show that L is not NP complete. Okay, so proof is very simple. Just by proof by contradiction. I suppose L is NP complete. Then there is a reduction. So there is a polynomial reduction such that polynomial such that you can write right L right polynomial reduct. Sorry, you can write 3Z because L is NP complete as 3Z or NP hard. So L can be reduced. 3Z can be reduction L. And if length is, let's say length is Y, then it will map to Y at most to the, let's say R, maybe C. Okay. Okay, so and right. So if this is true, okay. But actually we can solve L. We can determine L in the sublinear time. Sorry, not in the super sub exponential time. Okay, so this is like actually this is like the different statement. Okay, so you can just forget about this. Let's just try this. Okay, so suppose it's like the okay, so how can one determine L? Right, it's very simple. You first spend like O(n), right, and you spend like you can just spend like the 2 to the let's spend like 2 to the N to brute force determine 3Z. Okay. So you remember your N is like 2 to the square root N. So you can like spend of 2 to the square root N time plus 2 to the 2N time. Okay. But I don't want to write this, right? So this basically is big O 2 to the N. And I need to write in terms of N. So you can check that if N is 2 to the square root N, that means that N log N is basically 2 to the square root of N. And sorry on this. If capital N is 2 to the square root of N, then N log N will be 2 to the square root of N times square root of N. The log is base is 2. So it's 2 square root N square root N, so it's 2 to N. Okay, so this is n log n. You can try to write this in terms of like log n equals to square root n, and then you plug in this. But it's amazing that you can just, if you are smart, you just guess capital N log n will be this. Okay, so we can determine L, right, in a capital N log n time just using the brute force, right? We just brute force the verify all the possible assignment. Okay, but if this is true, then by previous, right, you can map this input y or the 3 set polynomial into y to the c. So you can solve 3 set in n log n time, but restricted n to be y to the c. Okay, so basically you get y to the c log y to the c. Y, so y is n, small n, right? So it's like you get nc squared log n. Okay, and then this is much more slower than n to the delta, which contradiction to the exponential time hypothesis, because this is much more smaller than delta n. Okay, so this is like the easy proof of Ladner theorem if you assume the exponential time hypothesis. And you can solve this by using the diagonalization, which is much more difficult. And there's two kind of proof that I will present it in a future video. See you guys next video.